Good afternoon. I'm Sue Lessica. And I'll be presenting today on my topic for the Nuclear Energy University Program fiscal year 2020 webinar for molten salt reactor materials. So this first slide here, the main goal is just to give you some examples on molten salt reactor types. As you can see, there's a lot of different companies that are looking at very different reactor designs. These computer renderings show you how much diversity there is in both the designs and in the companies interested. There's a lot of acronyms here. If you're involved in molten salt research, you're probably familiar with them. I'm not going to go into detail. You always have Google. Our next slide, the goal of this slide is to give you some numbers, to give you an idea of the environments that the materials for molten salt reactors are going to see with a comparison to our commercial PWRs. And so the bottom line of the table there is your numbers for PWRs with the numbers on top for some of the different possibilities for molten salt reactors. And so the main takeaway from this slide is to show that the maximum dose that we're looking at with MSRs is much higher than the traditional dose. And the pressures that we're looking at are much lower. So that's the main takeaway from this slide. The other part is you can see there's a lot of holes in the slide that have not been filled in. So some of these details are still being developed, still being released by the vendors. So the complete picture has not been drawn yet. So here we talk about when I was talking about the diversity in the reactor designs, there are fast reactor and thermal reactors designs for molten salt cooled reactors. There's different salts that are being talked about, chloride salts versus fluoride salts. Questions on would the fuel be liquid fuel or solid fuel? Another big question is on the lifetime, the planned lifetime for the reactor. Would it be a full 30 to 60 year lifelong reactor like we have for our LWRs, or would it be more of a prototype? Would it be 5 years? And of course, those differences make a big difference in material selection. So to further focus in on one of the issues with materials and MSRs, let's look at this corrosion chart. While we have some data on corrosion on different fluoride and chloride salts, there's a lot of variation in where they fall on this chart because of the varying conditions, the varying salts, and the different methods used. And so this is someplace that we need to focus on. So now focusing on one of the two different types of salt, the chloride salts. And here you have the redox potentials for a bunch of different elements in the chloride salts. You'll see that chromium is not on a really good place for the redox potentials for us. We usually depend on chromium in materials to be our method of corrosion resistance, and that's going to be a challenge for us in chloride salts. So so having other mechanisms to control the corrosion is going to be needed. And let's see here. Another issue related to the corrosion and in the mechanical stability is the doses. The doses that these materials can see can vary greatly, and so the material behavior over time is going to be also vary. So that's another thing that needs to be addressed. Right now, there are limited materials that are available. Here you have a list of them. We have alloy 617 has recently been added to the 4 that we had prior to that. And the issue here is that these materials were not optimized for MSR use. And their focus was on other types of reactors. And so because of that, they may not be the right materials for MSRs, particularly for advanced MSRs further down the line. And so that was one of the areas that was brought up in the technical gap assessment that was completed. Here's a picture of the reference. It's a really good reference on what the MSR, the issues around the MSR are. So with the NIA program, we are looking at long-term needs for MSR structural materials. The last 2 years, we funded awards focusing on materials for fluoride-based MSRs, both new materials and cladded materials. And so this year, we're going to look at it from another angle and look at materials for molten chloride salt fast reactor applications. And so we are looking for proposals to develop high performance new metallic alloys that could be used for welded construction of structural components for molten chloride salt fast reactors using a liquid fuel. And so here we are narrowing the scope of what these materials will have to withstand. Of course, that doesn't make it any less challenging. We are not focused on metallic materials at this time, so we want to focus on metals. And these are some of the issues that need to be addressed. High temperature strength, thermal stability over the long term, chloride-based salt compatibility, in addition to compatibility with the fuel that will be in the salt. And that goes hand in hand with resistance to the possible fission and transmutation products that will be in the fuel, causing embrittlement of materials. So radiation damage is also very much of interest, as well as mechanical properties. And of course, as always, fabricability and weldability are key here. We need to be able to fabricate components of whatever material comes out of the research. So here are some examples of innovative concepts that we're looking for, using ICME to use that capability in alloy development is a good idea. We've also, while it's not required, it's also, it could be very helpful to the PI and to the proposer to have interaction with MSR designers on their system requirements, so that the material is focused on particular MSR designs. So here's my last slide, has the contact information for both myself and for Sam Sham from Argonne National Lab, who's a technical POC on this topic. If questions come up after this webinar, you can reach out to us. And that is all that I have in prepared slides. So I'd be happy to take any questions.
Okay, if any of our attendees have a question, if you'll please type them into the GoToWebinar application. We'll ask them here in the room, and I will also open up Sam Sham's phone so that he can help address anything that might come up. Sam, can you hear us here in the room?
Yes, I can. Thank you.
Okay, great. Thanks. Okay, first question. How many awards are anticipated? And are you interested in different materials than proposed in the past? It says there is no way of knowing the details except the published abstracts.
Okay. As for the number of proposals that we will be funding, at this point, we don't know that because this would be funded with fiscal year 2020 funds. Congress has not yet made their appropriation. So at this point, I think it's too early to say how many there will be. I would estimate there would be 1 to 2, but it's too early for any sort of sure number to be said at this point. And yes, we are open to new ideas. That's the goal here. So whether it be a new idea or building on an old idea that hasn't been fully investigated, either one would work.
Are you interested in high entropy alloys or new nickel alloys?
If they would meet the requirements, we are interested in both. Is there anything you want to add to that, Sam?
No, I think that that is what we wanted, is that there are some performance criteria. We really don't know which will work for the molten core ISO, so we would like to have the help from the universities to sort of help us to address these challenging issues. Yeah, if high entropy alloy, if the PI can demonstrate that it will work, we love it. Yeah, we're looking for ideas. Obviously, that nickel alloy is known to be sort of relatively good for core salt resistance, but then we have the other performance metrics in terms of irradiation, etc. So I mean that there's no secret that this is a very challenging problem, and we are sort of really soliciting any and all ideas. Yeah, that's all I have.
Okay. Why are ceramic materials excluded from the work scope?
Because of our ability to only fund a few of the proposals, we're focusing on metallics at this point. So the future, we may focus on different areas, but that's our focus right now.
Yeah, and also that we're looking at structural materials, structural components applications. So obviously that ceramics will have a lot of those good attributes that we are looking for, but then that it brings in other issues in terms of fabricability, joining to other, ceramic components cannot be sort of placed in a reactor all by itself. It has to link to other sort of components. It could be metal. So that's the reason why we want to focus more in terms of metal for this time.
This person asked if you could please put slide 9 back on the screen. Perfect. Okay, what's the most important temperature range for these work scopes?
These would be high temperature reactors. I don't know if I could specify what's the most important temperature. Sam, would you be? I'd be hesitant to narrow it.
I don't know whether it's what the questioner was looking for. Is there some previous slides? This slide is shown on the screen, slide number 9. There's no temperature information. But well, I think that in some other slides, we said that we would like to have a good high temperature strength up to 900 to 950 C. That is a goal. If we can, well, for metallic system, we know that 1000 C is not something that is easily achievable unless that we go to refractory valves, and refractory metal will introduce other issues in terms of how we construct structural components. So I would say that 950C is the, well, would love to have it, but I would consider that as a goal. It's not a sort of a requirement. So anything sort of 950C and below, we would love to have it. The current materials that probably that my understanding is that some MSR developers are calling out for off-the-shelf or co-qualified materials like 316 stainless steel, so that the temperature range for that probably that you will be quite comfortable to use up to 650C for 316 stainless steel for this type of reactor concepts. So obviously that we want to develop some new structural alloys that can have a better temperature performance than the 316 stainless steel. So this is sort of the boundary. 650, we already have structural materials that we think that we can use. So any sort of new structural materials will probably have to be greater than 650C. So it's between 650 and 950, and then the 950, we're looking at that as a stretch goal. So somewhere in between will be what we're interested in. But there is more closer to the higher temperature side.
Okay, is the focus on the weldment, the joining of different alloys?
Well, I guess there would be two. For one, the first issue would be welding the new material to itself in order to fabricate components. That would be the first focus, I think, at this stage. You have anything to add to that, Sam?
Yeah. So the way that we construct reactor components, obviously that we can sort of make certain shape it out. Sooner or later that we have to use the welding process to sort of make things fit, etc. So I will sort of look at that in two tiers. One is that, well, if I would not worry about welding if I don't have the base metal that is capable to begin with. So the emphasis will be that, well, first find some sort of base metals that will sort of match up with some of those performance criteria and metrics that we put out. And if that is successful, then if that alloy is such that is not weldable, then we have an issue as well. So I sort of look at that as first is the base metal properties. And then if we can achieve that, then we ask the next question, is that weldable? So I will go about in sort of this order.
Is the focus on alloy 709, or could it be?
Again,
I don't know, but definitely the alloy 709 has very high chrome content. So whether or not that is optimum for chloride salt application, I don't know. But that material definitely has a higher temperature performance than 316 stainless steel in terms of the high temperature strengths like grip strength, etc. But I don't think that we have too much information in terms of corrosion resistance, etc. So that is part of the things that the proposers will have to sort of put together. So some logic in terms of why that they propose certain class of materials that they want to work on.
Yeah, so the focus again is not on a particular material, but a material that can meet the performance criteria. So we don't have a particular alloy in mind. We just want the focus on performance.
There have been awards on HEA and ODS in the past. Would those still be of interest?
Again, if they meet the criteria, they would be of interest. As Sam said with the earlier question on HEAs, if they can meet the performance criteria, we're certainly interested in them.
Would you consider a proposal with only theoretical work?
I think it would be I think a proposal with only theoretical work would be very challenging to to prove that it would be successful, part of the NEIP's goal is research and development to show that the concept would work. I think it would be a very challenging way to go.
Can you identify the radiation damage limits in DPA?
So my earlier chart had some data on DPA, so it could go all the way up to 200 DPA, as you can see on this chart, the third column from the right.
Is there any international collaboration allowed or encouraged?
I don't know what the rules are for the NEIP. That would be more of a...
Yeah, so we don't know at this time. Last year that we were given instructions and information that the UK, for the UK government, their researchers, but it can be on certain topics that overlap with the NUP.
Sam, we have somebody here that can answer that question for us.
Okay, thank you.
Yeah. To answer that question, international collaborations are encouraged as a general rule for NUPs. They cannot receive U.S. Department of Energy funding though, so it would be on a non-cost basis that an international collaborator could participate. Sam is right. The UK research councils have participated in past FOAs. My understanding is those discussions are still ongoing for this FY 2020 FOA.
Okay, thank you.
Are you looking for the development of new model alloy systems that can be engineered and code qualified in the future? Or are you more interested in engineering and processing of existing alloys so they can be code qualified right after the project?
I wouldn't limit it to either one of those. Again, we're focused on performance and the information that we have with research that's been done in the past. It's probably going to more be the latter, something that's requires further development. But again, we're focused on materials that could work in these environments. So whether it be a freshly, newly designed material or something that's been developed for another application that would work here, either one would meet the need here.
Is IASCC an important criteria to be addressed?
Yes, it is. Do you want to take this one, Sam?
Yes, obviously that the irradiation-assisted stress corrosion cracking, the phenomena is more well developed or understood or observed in, for example, in light water reactor and in other materials. So as far as the molten chloride fast reactor applications, that we have less information on whether or not that the IASCC is a degradation mode. So obviously that those are the type of things that we embedded in the performance metrics as to things that we are concerned about if they do happen. So therefore, that if that is demonstrated to be a degradation mechanism, then obviously we would like to have the structural materials, these new alloys that we are looking for to be resistant to those type of degradation mode. But I don't know personally and also it's material dependent. So yes, generally speaking, as what Sue says, yes, we are concerned about those type of potential degradation mode.
Okay, I think this will be our last question. How important is it to conduct in situ mechanical testing in molten salt environment?
Um, at some point, that testing will need to be done. If the PI proposes other methods that they think they could prove the concept that isn't required to do in situ testing, we're open to it, but at some point that type of testing will need to be done.
Yes, I think that, yes, I agree with you. In terms of in situ mechanical property testing in this molten chloride salt, it will be great to sort of generate those data, but also that as we all know that in terms of high temperature reactor applications, that obviously that the design lifetime, whether for small reactors or big reactors, it will be longer than the lifetime of a PhD thesis. So obviously that whatever that one does, you will just glean certain sort of sliver of information, and we want to glean as much information as we can, so we put together a story to understand that the material at the end of the 3-year award periods, that we have some sort of idea and some level of confidence that this material shows a promise, and we can do more of longer term testing through DOE program, etc. So whatever that can be done, I'm not going to say that yes, it is sort of absolutely required before the proposal work would be successful. So we're looking forward to have the PIs to put together a story. What are the sort of different types of properties, through some modeling, through some shorter term tests, etc., to sort of make the case that yes, that material will likely meet the performance metrics that we. Now, the performance metric, of course, that is, I don't know whether it's fully comprehensive, but it's a pretty long list. Obviously, that those are the sort of the type of things that as a sort of reactor designers that we worry about, and we want the materials to be able to sort of overcome those. But obviously that if we can sort of address them all, we like that. If it's addressed only 90%, well, we'll see how much that we can get out. Obviously that we understand that for all those issues, a 3-year R&D program is extremely challenging to be able to cover all ground.
Okay.
Okay, thank you. We will resume the webinar at 3 p.m. Eastern Time with FC 1.3, and that'll be in just a moment. Thanks, everyone.